5 years ago when we started Wayve, we had a vision for building autonomy that would truly scale. To be able to do that, it required us to fundamentally rethink how we build autonomous systems. This resulted in prototyping and understanding how to put machine learning on cars for the first time. Essentially, we've been able to leverage data to learn how to drive in a way that hasn't been done before. With a really lean sensor stack, so just cameras, and learning to drive based on what they see. No two experiences on the road are the same. That's why it's so important that our autonomous driving system is able to adapt. This is why generalization is so important. Generalization is the idea of learning a behavior or a concept and being able to apply it to new scenarios. Over the last year, we've been able to show that our autonomous driving system can generalize across two key concepts: generalize to different cities and generalize to different vehicle types. We were able to transfer our system from the passenger vehicle fleet to the van fleet with very little extra training data. Generalization is what lets us scale to the world. It means that we can enter new markets, drive in new cities, and we can adapt to new use cases as the demands of the world change. We can do this quickly, safely, and efficiently.
With the multi-city mission, we trained a driving model on purely London data and wanted to see how it would perform in cities all over the UK. The cities we went to were Cambridge, Manchester, Liverpool, Coventry, and Leeds. Being able to see such similar performance in such visually unique cities was very promising to see.
This is important because it means that we can learn to drive in one place and adapt to different cities at a really efficient rate that lets our system scale to the world.
Multi-vehicle generalization is really important because for people, when you learn to drive, you can then drive different cars, different vans, be able to get around in whatever vehicle you have access to. Our learning system should have the same ability. We took our model that we trained on thousands of hours of car data. We added around 80 hours of van data in order to train a model that could drive on both our vans and our original cars. One of the things that was most exciting about the results we got was that we showed that we could generalize in sim. We had shown that results we got in sim could be used and influenced the decisions we made in order to deploy a van on the road.
We've been able to learn the general concept of driving so that our system can drive both of these types of vehicles at the same time.
My responsibility is really the interface between a generalized driver model and the specific vehicle itself. We actually tried to work quite hard on developing a system that was more vehicle agnostic. We were able to really take a lot of the learnings that we had from doing the passenger vehicle to accelerate the rate at which we were able to provide safer features and to put together a more comprehensive safety case. Prior to putting any of our vehicles onto the public road, we find basically a safe testing environment, which would be like a vehicle proving ground. Basically build up your level of confidence that what you have made is working as you expect. We will also test things like the ability for the safety driver to make sure that all the ways that they can regain control of this vehicle are working 110%.
The fact is, driving in a city like London is extremely complex. You have so many different conditions happening. So we try to really address the problem holistically, looking at all possible conditions. For us to say that the system is going to be safe to be deployed, we're going to have to prove that the system knows and understands the environment, but also the system has the driving skills to be able to operate that environment.
I was very skeptical that this small amount of data would be able to generalize the performance that we'd seen on our cars, but The feedback I got from the drivers after the first day was they couldn't believe how good it was. A key takeaway from this is that a small amount of data in the targeted environment you want to learn can allow you to generalize a system that you have proved to work in one vehicle in another and potentially many others.
The van's performed really, really well. The way that the van takes the corners, the way that the van is so smooth. It was a really exhilarating experience, actually.
We saw our models negotiating roadworks that it would never have seen before. Negotiating buses and other oncoming vehicles, especially in the tight, narrow roads of London.
We were perhaps somewhat surprised by the result that we had with both the van and the passenger vehicle. They're very different vehicles in terms of the physical shape and size, but also things like the wheelbase and how they drive around corners. You know, as a human being, you drive two vehicles like a van or a passenger car in a very different way. The same AI model, or driver model, was actually able to work really well on two quite different vehicles.
We now want to roll this out to test with our commercial partners and prove that it works in a real-world scenario.
It's really hard to program driving culture, and that's why we think building a system that can learn from the world around it is what's going to result in autonomous driving technology that people will trust.
There is nothing more important than safety on our roads.
Autonomous driving is such an important milestone for society. It's going to give us safe, sustainable and accessible transportation. But not only that, it's going to launch us into the age of autonomy.
I do think we're going to change the world.